My name is James Norton. I'm a senior. I'm double majoring in computer science and applied math. And I've been doing research in digital audio with Ming Lin for about a year. And I wanted to start today with a motivation by an example that is very near and dear to my heart. And that is in making some drums and to kind of motivate what the state of the art is for modern music production. So this is a program called Ableton for sequencing music for a composer or a producer. And what I have here is a simple 2-bar loop, and I'll play that so that you can hear what I'm talking about. So, yeah. So you can hear that there's nothing complicated going on. But one of the techniques that I want to look at is this idea of multi-sampling, which has become a very standard technique in which the user combines several sounds from different sources in order to create one amalgamation of the input sources to create something that's bigger. So here on this bass drum, I have two different sounds. And so the one that we just heard is this one. And so now what I'm going to do is I'm going to play it with this other bass drum that I guess you can also hear. So with the other bass drum added in, this is what the resulting sound is. And I don't know if you can tell from the overhead speakers, but the resulting sound is actually a lot quieter now. And so I want to take a look at why something like that might have happened and use that as a motivation for why I'm researching this. So looking a little bit closer at what just happened, the key reason for why when we added sounds we got quieter is phase cancellation. And the reason for this kinds of thing is that the algorithm that they're using to create the new sound from the existing ones is simply to superimpose the waveform. In other words, this also means that they're interpolating the waveforms in the time domain. What this means is that they're looking at a single instant in time at each of the waveforms and then figuring out based on just that one unit of information where the sample should go. And the result looks kind of like this. And this is not what the waveform of a big bass drum looks like. And so what do we want to do differently? So what we want to do instead is create a system where given two input sounds to create a third sound that is parameterized by its proximity between the two inputs. So you can imagine that there would be one input and this sound moves continuously in a way that is perceived continuous from one to the other. And in this sense, proximity is some degree of similarity, which is both mathematically defined and, but most importantly, it still embodies a lot of perceived characteristics. And so the input that I've implemented on a high level looks like this. So let's take a look at what the input signal representation is. So all signals invariably come to us in the time domain, the domain in which we all live. And we can see that there's not a lot of information that we can gain from this. And so the main idea for moving forward is based on this concept that we can represent lots of information, like all of the information in the sine function, for example, as a single point in another function space. So in this example, we're representing that sine function by a single point. So in reality, complex sounds are the result of many frequencies. And so what we'll be doing is representing single points or instance of audio by the collective frequencies that they contain. And so what we're doing is we're taking a short window that can be described succinctly in the frequency space, and we're getting the power spectral density function for that instant of audio, and using a sequence of those to analyze the resultant sound. And so the place where things really start to get interesting is when we start to think about, well, what can we do now, given this characterization of a sound as a sequence of points. So what we're going to do is, since we're analyzing short chunks of audio, we're associating points with those. It would be nice if we could define some kind of notion of a distance or interpolation between those. And intuitively, what we're trying to create is, going back to the multi-sampling example, is the idea of, given some kind of inputs, we want to be able to create the intermediate form of two different sounds by using a more sophisticated representation. And so the main idea that this gets at is the concept of a geodesic, which is the shortest distance between two paths in a metric space. And so in order to talk about anything, like any kind of shortest path, we need a metric. I will say that the reason that we care about shortest distance is because for a resynthesis algorithm, if we know that at a certain time we're going to be outputting certain frequencies, and at a later time we're going to be outputting different frequencies, that we want to be able to move from one to the other without introducing as many artifacts as we can. And so in order to develop this concept of a geodesic even further, we need a notion of a metric on the space to describe, given one instant of audio, how different is it from another one? And there are multiple characterizations of this, and one such is related to the transportation cost function, which associates differences between power spectral density functions by how many frequencies you have to move to get from one to the other. And this has a very intuitive representation, which is that if you're currently at a low frequency, and from there you want to reach a mid-range frequency, you're not going to hit a high frequency in between because you would have overshot. And so, given this kind of characterization of the amount of work that we have to do in order to get from outputting one set of frequencies to a different set, now we can define a metric. So this is the Wasserstein distance of order 2, which describes the metric in terms of the minimum amount of work required in order to get from one frequency representation to another. And so this is typically solved using an optimization problem, but in the specific one-dimensional case that my problem is formulated, it actually has an explicit form, which is the following. So we can represent a geodesic, which is the shortest path between two different sets of frequencies using this characterization. And so, bringing this back to the approach of resynthesis and putting everything together, what we're doing is, after binning each short window of audio by its spectral power density function, we can follow the geodesics that are connecting adjacent samples. in the audio. And then based on where our intermediate points lie, we can then resynthesize these, which are connected in turn by geodesics. And this can be resynthesized using an inverse Fourier transform. And so I've implemented this system in a tool called Reactor, which I'm going to show you now. So this tool, Reactor, is designed for rapidly prototyping software instrument ideas. And so it's flexible enough to handle all kinds of processing. It's very similar to Verilog and hardware design in the way that it is that things are specified. And so the example that I want to show is the same example earlier of the two kick drums that weren't in phase, that were a lot quieter, even though you guys couldn't hear that they were a lot quieter, using the resynthesis approach. And so using the resynthesis approach, each one of these samples will be broken down into its spectra and then resynthesized. And this is what the resulting sound ends up being for these kick drums. And you can hear, or I don't know if you can hear, but there's a lot more low frequency content that is retained by doing the interpolation this way. And yeah, so I guess the future things we're looking at is doing user studies, other metrics, and other ways of resynthesizing the original signal.